Hello there, and I'd like to welcome you to the Chapter 4 review session, also called the Chapter 4 Study Guide. So all this information in this review session goes hand in hand with the information you learned from Chapter 3. So because of that, I'm drawing another volcano for your consideration. So there are 20 questions and 20 slides, so here we go. Question number 1. In the first question, you want to name what factors affect the viscosity of lava or magma. Can you name the first one? Starts with a T. Of course, this is temperature, so hotter lavas are going to be more viscous or less viscous. So that's less viscous, so they're not going to resist flowing. The second factor affecting the viscosity of lava starts with a C, and that's composition, of course, so silica content especially. And letter C starts with a D, and that's the amount of dissolved gas, which constitutes about 1 to 6% of a lava by weight. Question number 2, we have a picture of a nice, interesting person who's hard at work. So is this person digging in felsic or mafic igneous rock or lava? That is mafic, of course. It is basalt. Do you think compared to the felsic stuff, do you think there's a lot of SiO2 or quartz, or do you think there's a little bit? And the answer is there is a very small amount of quartz. Question number 2, we're going to have water on the left side and maple syrup on the right side, and you have to indicate which one is more viscous. And there we go. I've changed the background on you this time with question number 3, and we have some weird looking letters that should have some significance to you from a past chapter. So what you're going to want to do in this slide is that you want to draw an arrow underneath that line showing which direction are you going to have an increase in silica. And silica increases toward the felsic end. Okay, same thing, except now we want to consider, how do I increase the viscosity of your lava? Are you going to go toward the left or to the right? So since felsic lavas have more silica, they're going to be a lot more viscous or a lot more gooey. Okay, a third question. Now you want to draw an arrow indicating where you're going to have the most explosiveness. And of course, the more silica, the more gooey, the more viscous, the more explosive. Question number 4, we have a nice volcano that is outgassing, which means that it's releasing a lot of its gas, either prior eruption or during eruption. So because it's releasing a lot of gas, do you think this is likely to be an explosive volcano or not very explosive? So the answer is it's not going to be very explosive. So is this likely a felsic or a mafic composition lava or magma? And the answer is he's going to be mafic. Okay, another volcano, looks like the same type of volcano, but this time we have a lot of gas that's building up inside the volcanic cone. So, same question, what is its explosive potential? Is it going to be great or very minimal? And of course it's going to be great. Now because it's a great explosive volcano, is it likely to be a cinder cone or a shield cone? And there is your answer. Question number 5, we're now comparing the two types of lava flows, and we want to describe each. So can you describe an lava? So the word that I have down here is jagged. How would you describe pahoehoe? Okay, that is ropey. Are these felsic or mafic lavas or magmas? They are mafic, because they are basaltic, and therefore they form as basaltic lava flows. Okay, we're getting fancy now with the nice straight line, so we're going to compare all the different types of pyroclastics, starting with ash and dust. And over here on the right side, you want to describe probably by size. So ash and dust. We got big things, little things. What do you got? Okay, those are small particles. Next we have cinders, and that is a C. Okay, cinders are about the size of a pea. Next we have lapilli. Lapilli is the size of what? Okay, I wrote walnut. And then finally we're going to have the blocks and the bombs. Are they big chunks or little chunks? Okay, they are rather large. And I think on this slide somebody's bored. Question number 7, we have a picture of a volcano. And what is the arrow pointing to? So the arrow is pointing to its crater. Is this a shield cone? The answer is no, because it's not. This volcano's cone angle is too high to be a shield cone. So now I have a weird kind of drawing of a volcano, but apparently it looks like this volcano has blown its top. So the top of it was called the crater, but this bigger hole now is called something else that starts with a C. And that is caldera. And what happened to all the rest of the volcanic cone? Where did it go? So it probably laid out here on the valley floor or somewhere close by or even far away in the form of nice igneous layers, which you know as pyroclastics, extrusive igneous rock like tuff and welded tuff. Question number 9, what type of volcano is shown here, please? That is a shield cone. The composition of a shield cone is mafic. Is this going to be an explosive volcano? The answer is no, because the type of stuff that comes out of a shield cone is really just lava, predominantly. Doesn't mean to say that other stuff can't come out. Where are you going to find a nice, wonderful shield cone? So you can go on vacation on Hawaii and find that. Are there any famous names for any Hawaiian volcanoes? And the answer is, of course, there's Mauna Loa, Mauna Kea, and Kilauea. So we have an intermediate angled cone on this picture. It's not high angled, even though it might appear that way. So can you think of all the things that you might say about an intermediate angled cone? And I'm going to move on from there. This is a cluster of very small volcanoes, so what likely type are they? They are cinder cones. Question number 10, this is a halfway point. We have volcanoes all around the world, but in a particular region that goes around the Pacific Ocean, which is called the Ring of what? The Ring of Fire. And the volcanoes that you're likely to find here are stratovolcanoes or composite cones. Now this is kind of a little side issue, but here's why you have stratovolcanoes or composite cones. You have two plates, tectonic plates, that are subducting. One is thinner but heavier on the left, and the right side is basically a continental plate, so he's thicker but lighter. So to see that in side view, we have the left side of the plate, which is subducting or diving beneath the right side, which is the plate which a continent is made of. And all that red stuff is the magma chamber and all the other magma that's coming up into the volcano. So as my arrow shows, the left plate is subducting or diving beneath the right plate. And in the real world, this is called the Pacific Plate. And of course, that's the South American plate. And by the way, the mountain range that's formed, obviously, is the Andes. Question number 11, we have a volcano shown here. This is from the PowerPoint that I used in class. What type of volcano, please? That is a composite cone, and particularly this is Mount Fujiyama, or Fuji, from Japan. Now, Mount Fuji has a very particular shape and a very particular cone angle, which is intermediate, and it's made of all sorts of layered stuff. So that layered stuff is pyroclastics and lava. So that's why it is an intermediate angled cone with intermediate composition. And I just answered my own question. Okay, same picture from the previous slide, or 2 slides ago. So do you remember the concept when it's called when one plate goes down underneath the other that starts with the letter S? Subduction is what you're looking for. So why is it an intermediate composition magma or lava, and why is it an intermediate cone? Okay, the reason why is because the seafloor is made of mafic material, in other words, it's basalt, and the continents are made out of felsic stuff or granite. So when mafic mixes with felsic, it forms an intermediate composition lava or magma. That really is magma mixing, which is something you learn in Chapter 3. Question number 12. This is pyroclastic flow. What are some components of a pyroclastic flow? Well, it's made of ash or pyroclastics, obviously. But in order to flow, you got to have water. But there actually is a third component to a pyroclastic flow, and that's air. And the air basically makes it behave like an avalanche for all intents and purposes. So the question now becomes, why is a pyroclastic flow, or how is a pyroclastic flow different from a mud flow? And the answer is that a mud flow is confined to a channel, and a pyroclastic flow is not. But they both involve water. So here we have a volcano that you've seen before. Do you remember the name? Okay, this is Mount Fuji, and what is all that white stuff on Mount Fuji? That is snow, and what is likely to happen to that snow when the volcano melts, or erupts? Oops. Okay, the snow will melt, and that snow will be hot because the magma is hot, so that will form a lahar, or many lahars, which is basically a hot mud flow. Okay, question number 13. Here we have a nice volcano that is erupting from a cone, but sometimes we get lava that's erupting out of a crack in the ground. Do you remember what that's called? It's a 2-word answer. That is a fissure eruption. And typically fissure eruptions involve what composition material? Okay, there's your answer. Most of the time, basalt is erupting from a fissure to form a fissure eruption. So the best place to see that is if you ever go on vacation out to Washington State or even parts of Oregon. You're driving along, and all of a sudden in front of you is this great big huge mountain or great big huge thing, which is loaded with kind of straight picket fence looking columns, I guess. And what you're really looking at are different layers of lava. Okay, this thing is topographically is called a plateau because it's a great big thing that's real flat and you drive on top of it, but it's made of lava. So this is a lava plateau which formed from those fissure eruptions where lava was pouring out of the ground from a crack. And this picket fence stuff, if you look at it on the end of them, like looking at the end of a pencil, it's 6-sided structures which are called columnar joints. And this forms when basalt cools very slow. Okay, cooled mafic lava, but it's when the basalt does not move. It shrinks and it forms 6-sided structures. Compare and contrast with and Pohoihoi, which is basaltic lava that cools as it flows. Number 15. This is a volcanic eruption maybe in progress or it's about to erupt, but there's a big slug of cooled magma inside the crater, so that is actually called a lava dome. And if you see that, you want to run for your life because that means that the volcano is on the verge of erupting. Question number 16. We have a nice volcano. There's lava or magma that's come up into the center of it, but for whatever reason the lava or magma does not erupt. And over geologic time, the outside of the volcano is going to be eroded away, and what's left behind is the inside, which is called a volcanic neck. So some famous volcanic necks in the world include Shiprock in New Mexico, and of course Devil's Tower in Wyoming. So beautiful picture from lecture. So let's try to find some intrusive plutonic parts. So find the following. So where are my plutons? Well, it could form a pluton if all this magma cools completely under the ground first. So do you see any dikes in the picture? Are there sills? Are there stalks? Are there small little intrusive bodies that are massive? Okay, are there batholiths, which are much bigger? Okay, where is my volcanic neck, which obviously is going to be on the surface? And where is my stratovolcano? Okay, question number 18. We know this region as the ring of something, but where can you also find other igneous activity? Other places on the Earth to form volcanoes or igneous activity. So the first place is right here where two plates are pulling apart. This is known as the mid-ocean ridge. So you have extensive volcanism and extensive volcanoes in that region. You also can develop volcanoes in the middle of plates where magma is coming up into the plate. So those are known as hotspots or intraplate magmatic anomalies. So 19 and 20 are kind of hodgepodge questions, things that I've forgotten to ask. So let's now name the parts of the volcano. That is called the, and this is pre-eruption. That is a crater. Where the lava or magma physically comes out into the crater is called, it starts with a V, the vent. Here we have the pipe, and of course the magma chamber down below. And the final question is a true or false question because I really ran out of everything else. Is it true or false that a pyroclastic flow is the same thing as a nuée ardente, which is French for burning cloud? And of course the answer is yes. So that now concludes our Chapter 4 review session.